All right, so let's review for the test. So that quiz was just meant to give you a few extra bonus points. So I know it was worth 20 points and it was trivial, but I wanted to boost your quiz grade. Okay, so we'll just leave it at that. All right. Whoop. I didn't put my bag away. Warwick, who can't sit down? You can sit down up here, man. I don't want to displace you. I don't want you to feel uncomfortable by the different positions. All right, so today, well, before I go, are there any questions about projects or anything else? So before what we're going to do is just review briefly for the final exam and make sure everybody knows the final exam is on Tuesday, this coming Tuesday, in this room from 10:10 to 12:10. It's open book and closed notes. I'm going to go over what to study. I've already written it up. So I'm hoping everybody does well, because I feel like a failure as a professor when I look at the grades here. Not good. All right. And what I'm thinking is, wow, if they get like 90 something, their grades will be boosted on the final exam. But then I'm like, how often does that happen? Oh, one other thing, policies. Just because I know, even though I said this over and over again, the final exam will not be returned at the end of the semester, not even temporarily for you to review. So please don't email me and say, I thought I got 100 and you gave me a 91. I don't know what I did wrong. I'm very generous grading, and at the end of the semester's over, I put a ton of time into the class. That's when I have to draw the line is, no, I'm not going to individually talk to you and explain what you did poorly on the exam. If it was during the semester and I could talk to the whole class at the same time, just like we do on the midterm, that would be a different story. But after the semester's over, it's over. Now, wouldn't it be better if I took the time and explained it to you? Yes, of course it would. But it would also be better if I came to your house and tutored you individually. But we have to draw a line somewhere, okay? So don't ask me to look at your exam or I didn't do well, because again, I'm very transparent about the grading and all that, but I don't want to spend the time to explain to you what you did wrong and have you argue with me because you want a better grade or whatever nonsense. That never works. It almost always, the only thing I've ever done is lowered grades on students that have come and complained at the end of the semester. Oh yeah, I was too generous. Let me lower the grade. Okay? Really? No, it's okay. No, you wanted me to look at this, and you got a point. You did have extra points, but you know I took too few off on this other one, so your grade actually went down. Oh, yeah. Mm-hmm. All right, so now that we've done that little talk, let's go review. All right. So in chapter 9, well, first off, what are you going to review to study for the test? Because you know I'm really lazy. So what is it that I generally do? I reuse the homework and quizzes. You mean you actually wanted me to learn that? You're asking me the same question again? Yeah, I told you to study it, and that's not right. Really? It's not right? You ignored me and didn't study when I told you. All right, so study your old quizzes and homework. Yeah, then study the end of chapter problems. And I've gone over this. End of chapter problems. What's EOC stand for? What's TOC stand for? See how good you are with acronyms. Publishing. Table of contents. Yeah. All right. What's that? Text talk? Oh. Well, that's what they call it. It's like DOB, right? Date of birth. Or DB, dead body. MO, modus operandus. All right. Victim. Too many crime shows. So what you should study specifically. Now I'm going to tell you what to study in chapter 9. study study these things. Oh, and when you do these problems, when you study, take the problem, once you think you know it, write it on your whiteboard or write it on the board, write it on a piece of paper. Do not look at the solution and then try to solve it, because if you look at the solution, you look what I did, you look at the online solution, oh yeah, I know that. When you get into the test and all you've done is looked at solutions and told yourself that, oh yeah, I understand that, you will get spanked. Okay, you will leave the test not doing well and saying, that was really long. If you've actually worked the problems without looking at the solutions, you'll do well. Okay, so look at, in chapter 9, look at like the IV curves and associated circuits. Again, study the old quizzes and the homework. You know, like here's a parallel current source with a resistor and another resistor, plot the IV curves. There will be a problem on that. Okay? Also look at and understand all the FT, overdrive, widths, how to select all that stuff. What was the other one? GM, R out. Those kind of things. So when I ask you questions, you're not referring to the book and trying to figure it out during the test. Because then, man, that test was long. Also understand basic AC and DC calculations. So something like this. What's the voltage drop or what's the current that flows in the circuit? You know, where you have the square law equation. You know, you have to solve the quadratic, right? And you have to show your work. And also study example 9.5, because that's, I don't know if I'll ask anything on that, I actually don't remember. But that's basic to a lot of things, and there will be other diff amps on the test. All right, any questions on chapter 9?
I know it's in the book and it's on the lecture videos, but can you say something real quick about selecting widths?
Yeah. Well, let me ask you this. So the question was, can I say something about selecting widths? And the answer is yes. Does the width influence GM R out? No. As W goes up, GM goes up, and R out goes down. Does the width influence FT? Or overdrive? No. FT is dependent on the current and the overdrive voltage, right? The width is selected to source or sink a certain amount of current. So if you know you're charging a capacitor, I and C, if you have a specific dVdt, you know that sets your I over C. You know, where did you learn that? Where did you use that recently? The projects and your slew rate requirements, right? You had a slew rate requirement of 100 millivolts per nanosecond, or 100 volts per microsecond. And so that is, if you use like 6 micron wide devices and you need to drive 10 picofarads, you're not going to have the current needed to get the dVdt you need. So you adjust the W based upon that. Now, you can always use wider Ws. It doesn't influence the overall speed of the design, right? We just said it's independent of FT. But if you do that, you burn more bias current and your design dissipates more power. All right, any other questions on chapter 9? All right. Chapter 20. So chapter 20 is also kind of a fundamental chapter. It's current mirrors. So basically what I would study is the current mirror topologies, like the DC operating, you know, what's what, why do you make that MWS wide, etc. I would look at the beta multiplier. I'll probably give you a beta multiplier with some, oh, this this two transistors are the same size, but there's a ratio K larger in the PMOS, and derive the corresponding equation governing the operation. But hey, you've seen that already. You saw it on a quiz. You saw it, I think, on the midterm as well, right? So you have some beta multiplier. Output resistance. I may give you a problem with a regulated drain and ask you, say PMOS, and the NMOS that's in the book or whatever, and ask you to derive the output impedance of the regulated drain current mirror. If you know how to do it, it's easy. It takes you a few minutes. The test is easy. You turn it in. Score. I studied. I learned the material. If you didn't, you're going to be sitting there looking at the book, and I know what's in the book because I wrote it. And I'm going to, when you write your answer down, if you copied what was in the book, you won't get good points. But I copied what was in the book. Yeah, but you clearly didn't understand what you were writing. I'm telling you, these are going to be on there. Let's see, what else? Output resistance. You know, I might do a triple cascode. Derive the output resistance of the triple cascode. What is a triple cascode? This is a good problem because it says, do they understand what's going on? Because it's easy if they do. If they don't, then we'll find out. What's the output resistance here? What's the minimum voltage I have to have here in order to keep everything in saturation? Well, what's this voltage? 3 VGS. There's no VDD in here. I got a current source coming in, reference. Okay? What's this voltage? What's this voltage? 2 VGS. What's this voltage? VGS. So what's this voltage here? Each one of these transistors has a VGS in them. This says, do they have a clue what's going on? If not, I don't want them passing, or I don't want them getting a good problem here. What's this voltage? Well, let's see. The gate's at 3 VGS. There's a drop of VGS here, so that's 2 VGS. So what's this voltage got to be greater than? Really? Yeah. Simple problem. Very simple. How do I calculate the output resistance? Here's how I don't do it. I don't put small signal models for everything and try to do one big equation. I say, oh, the resistance looking down there is, and I derive the output resistance of the cascode. Then I've got this. Right? Then I've got this problem, which is just the same thing as deriving the output resistance of the cascode. So then what would it be? What if I just have this? What is the resistance looking down? Killing me. Does anybody not agree with that? You didn't cover it well in class. And if I have this, what is the resistance looking down? If I have this, what is the resistance looking down? Whoops. Yay or nay? Questions? Any questions on chapter 20? What are we going to do with chapter 21? Topologies, gains, and chapter 22 is a similar input, common mode, range. So what I might do, let's go to chapter 21. Oh, let's pick a topology. Or chapter 22 as well, I guess. Too much material. Where's the folded cascode? Isn't it in 22? Source cross-coupled pair. Cascode. What is it? No, it's in 21 or 22. I might have to break down and look in the index. See, this is why you don't want to, even I wrote the book and I'm having trouble finding stuff.
Shows us during the test.
Yeah. Folded cascode. Let's see how good the index is. If it's not good, we know who to blame. Folded cascode, 641. Folded cascode, 648. $714. Oh, there we go. Right there. Beginning of chapter 22. Here's a folded cascode. Wouldn't it be reasonable for me to, in the amplifiers, ask you, what's the input common mode range? What is the gain from the inputs to these two nodes, or the output, or this node, or what happens up here? All that, to make sure you understand it. Because why would I do that? You used it in your projects. I want to see, did they understand what they were doing, or did they just do monkey see, monkey do? So let's take a simpler version. Let's take one from chapter 21. Let's take this topology right here. I have the following. And I say, show your work. What is this voltage here? We'll call it V1. What is this voltage here? V out in terms of IS. What is this voltage here? Well, if we assume this is just I probably won't ask you that one, this is just R out cascode N, then you should be able to calculate each of these. Let's do one real quick. Let's do both of them real quick. Cool. So this or some variation will be on the test. You got me on video, you heard me saying it. If you don't know it and you have to figure it out during the test, shame on you. Okay? So now I'm going to go up, I'm going to draw, this is R out cascode P, and V out is equal to what? Is it positive? Yeah. Easy, right? Let's do V1. What's the VSG of this one? The AC VSG? 0. So how much GM VSG flows in this device? 0. So I replace that device with an R out P. Because I look up there, you scared me a little while ago when we were in chapter 20. I look up there and I see just a resistance to AC ground. What's the current coming in? IS. Down here, I have a current that goes down like this, which I'll label in a moment, and another R out P. And then down here, I've got R out cascode N. What is this volt? How do I label this? I'll start you out. It's GMP times. Okay, so what is the AC voltage there? So VSG is V1. Does anybody not see that? Where's V1 on this plot? So tell me what to do. We can do it the hard way and we can do it the easy way. Let's do it the easy way to begin with. What do I do? KCL. IS equals V1 over R out P plus an easy way is to recognize, hey, this is a huge resistance, so the amount of current that flows in this path is going to be 0, or basically 0, because I've got such a huge resistance down there. Do I have to do that? Nope. I can make it more complicated. If I do, it's just like finding the output resistance. I still end up with getting the same approximate answer. So when I said that, tell me what I'm talking about. I inject a current. I have this voltage V1. Then I call this voltage Vx. And what do I know about the current through here? It's, okay, I'll write this and you tell me if you agree with it. It's IS minus V1 over ROP. And that's Vx. Now I have enough to solve everything, but again, if you want to do that, you'll get an answer that's almost the same as if you assume the current through here is 0. But you can do it, it's easy. Because the current that comes in here is IS, the current that leaves is V1 over ROP, and what's left goes through these two branches down here. That's IS minus V1 over ROP. And that gives me my Vx. So Vx is equal to IS minus V1 over ROP times R out cascode. I have two equations, two unknowns I can solve. But if I solve here, then I get IS is equal to V1 times 1 over ROP plus GMP. Or in other words, V1 is approximately, V1 over IS is approximately 1 over GMP. And that makes sense because the resistance looking in there is R out P, the resistance looking down is GM, 1 over GM, and 1 over GM is going to be a lot smaller than R out P. So I could have done that intuitively. But again, this will be on the final. Some like this, or folded cascode, or maybe even both will be on the final. Got it on tape. Liar! Oh yeah, on tape, yeah. All right. Okay. Any questions on chapters 21 and 22? Okay, I don't think I put anything on chapter 23, the voltage references. Chapter 24 and chapter 22. Stop forcing me to learn. compensation frequency response op-amp topologies. Be able to answer questions about how do I increase the speed of my op-amp? Okay, that's a real good one. And if you say anything about F2, you're wrong. F2 is secondary. To increase the speed of the op-amp, you increase the GM of the diff pair, or you reduce the compensation capacitor, because the speed is GM over 2 pi cc, period. Now, if you run into problems with stability where you increase the unity gain frequency by increasing GM or reducing cc, what do? How do you make the op-amp state more stable if you've increased the unity gain frequency? Okay, wait, so here's my op-amp topology. This is the unity gain frequency. This is the DC gain. What was the 3 dB frequency then? Gain bandwidth product, right? And if I increase the AOL DC and keep the unity gain frequency the same, it just drives this up and lowers the 3 dB frequency. This could be 1,000 hertz, could be really low. When I put it in the feedback configuration, it comes out here and falls down. If I move this up, this is GM over 2 pi cc. Now, I had a student a year or two ago that I tried to get an internship with, and he got a phone interview. And they asked him, how do you increase the speed of an op-amp? And he goes, hello? There's no deep thought. That's like a gimme question. Does everybody follow? That's the answer, independent of any op-amp topology. Okay, so now, if I have F2, F2 causes the pole to roll off. What's the problem with that? The phase starts rolling off a decade before that, which will cause the phase shift at the unity gain frequency to drop. So in order to make that phase shift less of an issue, I need to move F2 out. How do I do that? Increase the width in the output stage, increase GM2, because F2 is proportional to GM2. Okay, so last lecture I talked about increasing the load capacitance. What does increasing the load capacitance do to the frequency response and why? If I increase, remember I gave you the example where you're going to appear incredibly intelligent, where you see some oscillating meter and you go up and you put a resistor in series with the measuring equipment and it stops oscillating, they go, wow, you're smart. What does increasing the load capacitance do to the frequency response and why? Okay, I'm going to tell you one more time. This is something you should know, and then I'm going to show you in the equations. Increasing the load pushes F2 down. If I push F2 down, that causes it to interfere or interact with the unity gain frequency, or the phase shift adds to the phase shift at the unity gain frequency, making it more unstable. Prove it. I don't believe you. Prove it that increasing the load capacitance pushes F2 down. All right, let's go back to chapter 21 in our summary. Pole splitting summary. F2, GM2 CC, 2 pi CC1. Where's the load capacitance in here, in this equation? It's C2, right? So if I divide the top and bottom by CC, so this is then C1, C2 over CC, and C2. If I increase C2, you can see that it's going to cause F2 to go down. If I increase the load capacitance, it's going to cause F2 to go down. Does everybody follow that? So if that happens, I need to increase the GM2 to push F2 back up. That's why I increase the widths. and thus the current that flows in the output stage. Any questions? To me, it's super clear. One more comment. Explain in your own words how the right half plane 0 comes into B. What causes the right half plane 0? Explain in your own words. Yeah, you say the voltage swing on node 1 feeding through C sub C directly to node 2. How do I reduce that effect? I can put a resistor in series with CC to attenuate it, or I can block that forward path, which is what I do with the indirect feedback. And one more time, if you're asked in a phone interview, how do you increase the speed of the op-amp, your brain shuts off and you say, it's GM over 2 pi CC. You either increase GM or reduce CC. No deep thought. All right. Let's see if there's anything else we need to know about here. You guys feel like you learned something in this class? Are you going to, after the semester's over? All right. So, let's see, is there anything else we should study for the test? One other minor thing. Explain in your own words why we look at AOL beta equal to 1 and angle of AOL beta equal to 180. Explain in your own words why we look at that for stability and what are the assumptions. What do you, I mean, it's easy, right? What did we do when we went over that? We wrote the feedback equation, AOL divided by 1 plus beta AOL. When does this blow up? That's the closed loop gain. Beta AOL is equal to minus 1. Minus 1 is a magnitude of 1 and an angle of 180. Does everybody see 1 minus 1 is 0 in the denominator, 0, and it blows up? And then we said the worst case situation is when beta is equal to 1. Then we can look at AOL's 1 and AOL's beta. We said that if the gain is greater than 1, we're feeding back less of the signal, and so it's easier to get a stable op-amp. So if our gain was 2, beta would be 1/2. Because what is the closed loop gain? It's 1 over AOL plus beta. If AOL goes to infinity, the closed loop gain ideally goes to 1 over beta. So if beta is 1, the gain is 1. Closed loop gain is 1. If beta is 1/2, the closed loop gain is 2. Sketch an example of an op-amp with a beta of 1/2. Value that's fed back here and subtracted from the input. There's my input, Vn. This is my summer, which is the diff amp on the input. Here's my beta of 1/2. So this is 1/2 V out. There's my op-amp transfer function, the AOL, this thing. And there's my output. Okay, any last second questions?
Just in general.
Yeah.
I had one about injecting the ceiling current. It's on page 273.
273. I like it, you're getting your money's worth.
So in general, if we had like ignoring the resistor to be in VDD in figure 9.6a, if we just ignore like the scaling and injecting current for now, and just have the resistor, like ignore the resistor VDD, if we increase VGS, that increases ID, and that decreases the drain voltage.
Yep.
So VDS decreases.
Yep.
Right? Now, if we were to inject current.
If you inject current in here? Yep.
Then that's increasing ID, correct?
Well, it'll increase it a little, right? Because when you look at the curve, say you're operating right here, if you try to inject current,
right,
You're gonna move up on the curve because VGS is staying
So
constant.
VDS is going up with
Yeah.
ID,
Yeah.
and VGS is constant.
Yep. Yeah, when you inject the current in all of these, the VSG or the VGS isn't changing.
Because yeah, the difference from what I said initially was when we increase VGS, it increases the current, but it decreases the drain voltage, it decreases VDS.
Mm-hmm.
Here, we're keeping VGS constant, and it increases VDS as ID increases.
Yep.
Okay.
Yeah, if you pushed, it's very, you don't, if you think about it, if you push pressure in here, you put current in here, the pressure's got to go up. If you pull current out, the pressure's got to go down.
Right.
This, the whole point of this is just so you don't think math. You think, well, what's happening in the circuit? Just like if I increase VGS, as you just said, that's going to cause more current to flow and cause the pressure to drop for a fixed resistance.
And then also, so if we were injecting current, then our drain voltage goes up, correct?
Yep.
And then, so VDD minus the V drain.
Less current would flow through the
Less current flow
resistor
through the
because it would be coming in or supplied from the external source.
Perfect.
Any other questions? You know what to study for the test. You got it on record, what to study. Have a good day. We'll see you on Tuesday.